biogeochemical, biological, and chemical, and the geochemical system links the land and open ocean. If you look at the global climate system model, these components is actually very hard to be included. At the same time, this is the coastal ocean characterized by very complex circulation. It's hydrodynamic, if you want, and very much abundant river and the groundwater input. That's the input from the land. A very dynamic sediment boundary layer, and of course, very high productivity. And if you look at all the gradients from the shoreline to the offshore, you see very large gradients in terms of chemical elements and biological parameters. And the surface pH is controlled by the ENSO project, the CO2 level in the air and the buffer capacity of the seawater, essentially the carbonate system in the water. One of the most things we're concerned about is this saturation state. That means that the capacity of the biogasification. So essentially, we'll see pre-industrial area and the decrease of the omega. That's the saturation state of the calcium carbonate. And I guess.
Last climate cycle. Then you see the actual measurements that we've done in the ocean, and this is just one example of one of the IPCC scenarios. But you can see that we're getting way out of any of the measurements that we've seen for many millions of years. On the left here, this has nothing to do. This is the present day. You'll see the date here, 2007. This is something that informs the regionality of some of the modeling that we're doing. It's something that we found that's very sensitive to developing scenarios of acidification. Is you saw from Minhan's figure of how constant, or you see the Mauna Loa increase. The atmospheric CO2 is actually quite constrained within a narrow boundary. You move up into, certainly in above the equator, you see these enormous swings of, well, they are very important swings anyway, certainly for CO2 flux studies, but also for determining. But it's something certainly relevant to policy, and when you're speaking to your policy makers or you're communicating in education, is how long this will last. I mean, David Archer said, actually quite a long time ago, the lifetime of fossil CO2 is 300 years plus 25% that lasts forever. You've got to realize that even if we stop now, it will take 100,000 years before pH gets down to the levels it was before 1860. But this just shows you the processes. This is the PCO2 when we started this experiment. We're now presently going up here, we're coming up to 400. If we just take a random 2,000 gigaton fossil fuel relevant fossil fuel release, our PCO2 will go up to 800, and then we will stop. We'll
and the southern coastal waters. Most data in southern coastal waters, like this data, they are all lower than the red line. Red line indicates air PCO2, results in high PCO2. Why low PCO2 in the southern coastal waters? This is related to phytoplankton use. Phytoplankton use CO2 by photosynthesis. Remote sensing graph show here southern coastal waters phytoplankton biomass is very high, the red area.